Okay. Hi, everybody. So today, right now, we're going to talk about combining NetPyNE with reaction and diffusion from Neuron. So we'll look at how we can sort of move from chemical dynamics at the sort of scale of single cells and in the extracellular space, and how that can sort of build up and affect network dynamics. So let's hide this. Oh, what the hell? Oh my God. None of my keys are working again. Okay, there we go. Okay, so just an overview of what I'm going to talk about today. So we're just going to, so Robert the other day gave a great sort of overview of reaction diffusion, sort of the fundamental concepts, and how to implement them in Neuron, but I'm just going to recap that sort of, that bit today. The main points being that we want to keep in mind when we make a reaction diffusion model are where are the dynamics occurring, who is participating in those dynamics, so what ions or proteins or chemical species or whatever floats your boat. And the last thing is what are the reactions, so how do we define those dynamics mathematically. And then we're going to go into detail about how to implement RxD models in NetPyNE. So basically, I'll go through at least one of the examples that we did a couple days ago in Neuron and look at how that translates directly into NetPyNE syntax. And so we're going to see the same sort of declarative language or declarative grammar that's used in all the other NetPyNE model specifications and use that for reaction and diffusion. And then we're going to take a look at some RxD examples in NetPyNE. So that part of that will include interfacing with the underlying neuron objects in the NetPyNE model. You may be surprised to learn that NetPyNE doesn't do everything yet. So occasionally it will be useful to dig into the neuron objects that are sort of laying underneath the surface of the NetPyNE model to do certain sort of custom-y things that you might want to do. That'll involve combining Neuron's functionality and NetPyNE's. And we'll also look at an example of a network model that has subcellular chemical dynamics and how those subcellular dynamics affect network dynamics at the circuit or network scale. So I'm just going to start with the RxD concepts. The first question that we have to ask ourselves is, where do the dynamics occur? And these are defined by RxD regions. So the common ones would be the cytosol for intracellular space. You could break up the intracellular space even further into cytosol and organelles. You might have a model that wants to separate out the nucleus or the mitochondria, or we'll see later the endoplasmic reticulum from the rest of the intracellular space. And then we also can define the extracellular space as a region. It's worth noting that the extracellular space is separated from the intracellular space by membranes, and those membranes are defined by neuron sections. Whereas if we want to talk about organelles and the cytosol, these are going to be fractional volumes that are distributed or separated by membranes, but they are separated by what we're going to call distributed boundaries. So there's no neuron sections to define these intracellular compartments. So we're going to use this distributed boundaries concept to define them instead.
Craig, that's not necessarily the case. You can define boundaries, or I think.
I don't know why I just tried to turn my microphone off. So, yeah, you're right. So you could define, I think, like a shell within the cell, but would that be with sections?
No, not with sections. That's a separate syntax.
Okay. So yeah, I hope let me know if I don't cover it, but I think later on we'll see how we can separate like the endoplasmic reticulum from the rest of the cytosol with this distributed brown boundary thing. Oh, okay. So the next one is who's involved in the dynamics, and those are RxD species. So these could be ions or molecules or proteins and enzymes. The little magic carpet looking thing down below is IP3. We'll look at that in relation to calcium dynamics in the network model later on. And then there's the question of what are the dynamics? And this is a little bit more complicated. There are sort of three varieties. We can have chemical reactions that occur within a region. Those are specified by RxD reactions. There can be reactions that occur between regions. You might think of exchange of ions across a membrane or via voltage-gated ion channels or active ion pumps. These would be defined with multi-compartment reactions. And you could also have changes to species concentrations that are other than reactions. These would be a rate. And this could be you're either eliminating or replenishing a species from a compartment. So you might imagine you're infusing some chemical into the extracellular space, or you're eliminating some molecule or some protein from the extracellular space somehow or another.
I had a quick question.
Sure.
On the previous slide. So so for example, the multi-compartment reactions, we're talking about exchanges of ions across membranes with voltage-gated channels. That is, so for example, with Hodgkin-Huxley, that is kind of modeling an exchange with like sodium and potassium. So is that redundant with this, or like how do those react if you have both occurring at the same time, like in the same model?
Well, so by both, do you mean like both an exchange of potassium and sodium, or both as in like you have Hodgkin-Huxley like mod files that are inserted into the sections, or like RxD defined?
I think he's referring to the fact that you can have RxD defined Hodgkin-Huxley channels. It would be probably a little too confusing to mix those with mod defined Hodgkin-Huxley channels, but not impossible. Probably more frequent is the usage of pumps, ATP consuming pumps and the like for the membrane in RxD, but you could do all of the above. It's a bit of a redundant, a different way of doing it, and somewhat slower in RxD actually, but might integrate everything better.
Yeah, and yeah, like Bill said, you can have both going on at the same time, and actually NetPyNE kind of like simplifies having both of those going on compared to the Neuron framework. But yeah, you'd probably want to choose a paradigm for your model and stick with it, just for the sake of simplicity. But yeah, like Bill said, also implementing these things in RxD is a bit slower than implementing them as mod files, but you get the benefit of interacting with the extracellular space and diffusion and all that stuff. So it's a trade-off, and it's a choice you have to make based on
redesigning the shoes, huh?
Right. Okay. There are a couple other RxD concepts that don't quite fit into the who, where, and what framework. So you could have parameters. So these are values that are defined differently in different regions, and they're fixed in time. So you might, want to have a parameter that defines the boundary of the extracellular space, and you have, its value is 1 at the boundary of the ECS and 0 elsewhere. You could also maybe have a parameter that, distinguishes the soma from the dendrite. So, the value of the parameter is 1 at the soma, 0 in the dendrites or everywhere else. You could also have states. These are state variables, like the gating variables from Hodgkin-Huxley. So, you know, M gate or H gate. And these are allowed to change over time via relationships with either RxD rates or multi-compartment reactions, or I think regular reactions work as well too. So now just into the kind of meat and potatoes of this talk, right? How do we take something from RxD and move it into NetPyNE? So we're going to start with regions. And it's also worth noting that when you make these things, when you build these models in RxD, the order in which you build them matters. You need to create the regions before you can put the species in the regions, and before you can define interactions between the species. In RxD, or NetPyNE rather, since it's all in this declarative format, and NetPyNE goes and makes the model for you after the fact, you're not beholden to keep this order, but it is best to just for sort of logical flow to things. So even though you don't have to put the regions before the species, you probably should anyway. But okay, just to sort of go through this. So in each of these cases, we'll have a sort of biological thing that we're talking about. What does it look like to implement it in Neuron, and then what does it look like to do the same thing in NetPyNE? So here we're defining the cytosol. This is imagining that there's only like one intracellular compartment defined by the cytosol, and you know, in Neuron we would specify the sections that we're interested in, the neuron region that we're talking about, and a name for the region. In NetPyNE, we would use a dictionary like always. The name of the dictionary entry is going to be the name of the region. So rather than just specifying the sections, like in Neuron, you can specify the cells and the sections. So if you have, like we were talking about, some cells that use RxD, other cells that don't, you could specify that in this cells entry to the dictionary with a list of cells. Just like Neuron, we're going to say which sections, and we also want to define the region. You don't need to give it a name; it'll automatically name it site. Sorry, did somebody have a question? No? Okay.
Sorry, Craig. Actually, I do.
Okay.
What about the populations?
So the populations are you're going to define the same way you would in NetPyNE otherwise. So later on we'll take a look at a full RxD plus NetPyNE model, and it's the same conventions to define the population.
Sorry, Sonia, if you can define populations here in the cells field, you can do that. So you could say cells of the S population or whatever, and include that in brackets the same way you are recording when you are recording voltages, for example.
Oh, okay. Perfect. Thanks.
Okay, cool. Okay, so this is like a much more, or a slightly more complicated example where we have two intracellular compartments. One is the cytosol, the other one is the endoplasmic reticulum. And you'll see that in the Neuron convention, we'll define the cytosol with sort of similar syntax to before, where we'll say, you know, h.all_sec. We want it to be all the sections inside the neuron region, you know. But rather than, so we need to specify the geometry. And this is where that fractional volume business comes in. So here we're going to make it, the cytosol takes up 83% of the intracellular space, the surface fraction of 1. We also give it this name, cytosol. For the endoplasmic reticulum, similar thing. We'll use a fractional volume. The endoplasmic reticulum is only going to take up 17% of the intracellular space. And then we have to define a membrane between the two, even though there is no membrane from the neuron sections. So again, we want this to be in all the sections. We're going to use a distributed boundary for the geometry, and we're going to call this the site ER membrane. And then below is just how we translate that into this declarative format. So see very similarly, there's an entry for geometry in the site and ER dictionaries, and basically the arguments that are passed to the fractional volume are passed as arguments to the dictionary, if that makes sense. So you'll see like geometry, the class of geometry is a fractional volume. The arguments that are going to be passed to it are the volume fraction and the surface fraction. And then for the membrane between the two, the class is going to be a scalable border, which doesn't appear up the top, but that's basically the same as the distributed boundary. And then we're going to pass some arguments to it. An important one being that it's not on the cell surface. If it were, that would be the lipid bilayer between the cell itself and the extracellular space. Okay, another type of region is our membranes, specifically the membranes that define the cells, not the membrane that would, say, separate the ER from the cytosol. Pretty simple syntax. Again, this is going to, in neuron, this is going to be related to all the sections. We're going to name it mem. And for the geometry, it's going to be rxd.membrane. That's like a built-in function to take care of that for you. And this translates pretty directly into the NetPyNE format, where, again, we want to do all cells, but like we were mentioning earlier, we could define it for a subset of cells and a subset of sections for that matter, although all cells have a membrane of some sort. So for the most part, you're going to want to do this for all cells and all sections. It doesn't have a neuron region. You'll see right here. So this actually is like the membrane takes up no volume essentially. It's just a barrier between two regions. And again, so the geometry, this RxD.membrane call is built into Neuron, so you can just specify that this is a membrane in the geometry field. A big one for read the regions is the extracellular space. It's a sort of special class of region in Neuron, as well as in NetPyNE. And actually the syntax is a little tricky. So for the extracellular space, you want to define the X, Y, and Z bounds of the extracellular space that you're going to stick your cells into. In Neuron, you start with the low X bound, the low Y, the low Z, and then the high X, the high Y, the high Z. And, we can specify them in any order. Down here you see in NetPyNE because it's a dictionary. So here we did X low, X high, Y low, Y high, Z low, Z high. Either way. DX is going to be specifying the binning isn't the right word. The spatial sampling frequency isn't either. But basically, how small are we going to chunk up the extracellular space to compute the diffusion of stuff? So here we're going to use 25 microns. So we're going to take this 400 by 400 by 400 micron extracellular space and break it into 25 by 25 by 25 voxels. Voxelization would be the word I was looking for, I suppose. Two other important parameters with regards to the extracellular space, the volume fraction and tortuosity. I don't know if this was covered too in depth a couple days ago, but the volume fraction is what percentage of the extracellular space or what percentage of the volume of tissue is occupied by extracellular space. So 22% of the tissue volume, or the model volume, is extracellular space. This has a big influence on the diffusion, and the other is tortuosity. So tortuosity is a measure of how hindered is a diffusing molecule or ion in the extracellular space. So if there's a lot of extracellular matrix molecules hindering the path of a diffusing particle, the tortuosity is higher. If there's nothing in the way, there's not much in the way of extracellular matrix molecules, it's going to be lower. And if you look down at the NetPyNE implementation of this, it's a very close mapping to the Neuron implementation. Other than in order to make sure that you're using the extracellular type of region, you just have to include in your dictionary that it is true this is an extracellular region. Also, I didn't mention this earlier, but it's worth noting. Let me see if I can find an example from back here. So the regions, as well as the reactions and the states and all of these RxD objects are going to be dictionary entries in RxD params, which is a part of NetParams. So in this case, this would be an instance where you only have one region that you're going to talk about. So you can just, equate RxD params, brackets regions, to this one dictionary, right, for the cytosol. Whereas in this example, we have 3 different regions that we're concerned with. So I've created an empty dictionary and then populated that dictionary with an entry for cytosol, for the endoplasmic reticulum, for the membrane, and then RxD params, the regions are equated to this dictionary up here. So it's just a matter of sort of keeping things clean. Okay. So now for the species. So species is anything that is going to diffuse or react. For the biological thing that we're interested in, we'll look at IP3 with a non-uniform intracellular distribution. Picked non-uniform because it's a little more interesting, and we might as well cover that while we're here. So this is from the example, the diffusion example from a couple days ago. In Neuron, we define a function to specify this non-uniform distribution. So up here we say, you might recall that there are nodes in RxD. Nodes are sort of the RxD analog to segments, but nodes also exist on a segment. So what we can do is we can say, if we're at a node, the segment that corresponds to that node, look at its X position. That's going to be a value from 0 to 1. If you recall, segments have a position from 0 to 1 that maps onto an actual distance that would be the actual length of the segment, or section rather, sorry. So this conditional statement is basically saying if we are between 40% and 60% of the length of this section, set the concentration to 1 millimole. Otherwise, the concentration should be 0. And then we define the species, IP3. The first entry, or the first argument, is the region that it lives in. So it's the cytosol. D is the diffusion constant. We give it a name. And then in order to implement this non-uniform distribution, we pass this function myInitial to the initial value for IP3. Down below, we do an incredibly similar setup, but rather than define a function, we use a string that will get executed as that function. So basically we've collapsed this if return else return statement into a single line string. So one, if the distance of the segment is, between 40 and 60% of the length of the section, otherwise 0. And so we can just pass that string to the initial value for this species IP3. Does that make sense? Everybody feel good? Okay. So here we can look at a even more complicated distribution for a species. So this is, we're going to try potassium. It'll have one value intracellularly. So all cells have the same initial intracellular calcium or potassium value, whereas in the extracellular space, it'll be non-uniform. So here's the neuron version. This is using a lambda function rather than defining a function outside of the call to RxD species, but it's the same idea where but first we have to check if this is intracellular or extracellular. In the context of this, where this example comes from, all of the intracellular nodes are 1D diffusion nodes. So we can check to see if the node is a 1D node. If it is, that means that we're intracellular, and we can set the value of the concentration to 133. Otherwise, we want to set it to be oh my God, did I copy this over incorrectly? Probably, yeah. No, I did. Avert your eyes, have a look at the NetPyNE version because it's basically the same setup. So again, 133 if we check to make sure that the node is intracellular, and if it's not intracellular, we want to place it as 10 if we are within this 25 micron radius of the center of the ECS. So that's this node.x3d squared plus node.y3d squared plus node.z3d squared. So if that radius from the center of the ECS is less than 25 microns, set the initial potassium concentration to 10 millimole. If it's outside of that sphere, set it to 3.5 millimoles. And then the usual stuff, D is 2.6, the charge of potassium is 1. The complicated bit is this initial business.
Yeah.
Okay, so we've got RxD rates. So we saw this example yesterday where you have this regenerative signaling dynamics, and that's defined by this above equation. The D gradient squared y, that bit's covered by diffusion, but the rate that we want to look at is the second half of the differential equation, k times y alpha minus y times 1 minus y. And we saw the other day that we can implement that as an RxD rate with this sort of syntax. Y here is a species, K and alpha are parameters. So similarly, we can implement that in a string. The sort of main difference to focus on here is that we're specifying in this string the region that the species Y lives in. So this Y bracket site shows up rather than just Y up here. But otherwise, it sort of follows the same format. You define the rate as a dictionary. I call it Y rate. The species, you specify the species that you're concerned with, just like up here. The first argument is Y. Here, our dictionary entry is Y site, and the rate is going to be this string up here that defines the dynamics. And And I think this is finally multi-compartment reactions. These are gonna. Oh, I'm sorry. Yeah, these are gonna follow the same procedures as reactions as well. So if you get this, you should be able to get reactions too. Here we're gonna look at sort of a Hodgkin-Huxley-like sodium current. If we look at the Neuron Rxd code, we have two sort of important. They're not really variables, but here, GNA bar is a constant, M gate is an RxD rate, or I'm sorry, state, as well as H gate, as well as VIR and VOR, but that's not important. The important thing is that we have this reaction is going to use intracellular sodium as the product, extracellular sodium as the reactant, and then it's going to use this this equation to define the dynamics between the two. Whether or not this is mass action is something you can set. You have to specify a membrane for the multi-compartment reactions. So since all multi-compartment reactions take place between compartments, there has to be a membrane that separates those compartments. And you can also toggle whether or not this affects membrane flux. So does the passage of charge generate a current, or the passage of the ion or species or what have you, which sodium for sure does. So in NetPyNE, we see something similar. As I said, these M gate and H gate are states that have been defined someplace else, as is this volume ratio. Those are states defined someplace else, and sodium has already been defined as well. So and here we're saying sodium in the ECS, sodium in the cytosol. And for the dictionary that defines the reaction, you have to specify separately the reactant, the product, and then the forward rate. At least in this context, you could also have a backward rate. And we're just using these string formatting to place these other strings into the equation. You could perceivably write out one long, terribly confusing string to define rate F, but keeping these separate parts and separate variables sort of helps keep things clean and readable for the most part. And again, you have to specify a membrane. We want membrane flux to be true. Custom dynamics is also true. Whether or not it's mass action, that's defaults to false. So didn't bother setting it here. And then we pass that to RxD params, brackets, multi-compartment reactions. Okay. So here we're just going to run through one of the examples from the other day where we had the regenerative signaling. Just to show you exactly how sort of things map from one to the other, right? So we start off with the cell properties. So over on the left, we instantiate a section, set the length, the diameter, the number of segments. Whereas over on the right, that's all sort of wrapped up in the population parameters and the cell properties. And I'm sure you guys have probably seen that ad nauseum in the last couple days. So no sense in taking too much time with it. And then this is the mapping for the region. So we have the definition of the cytosol region in Neuron, and the definition for it in NetPyNE over on the right. Very similar syntax other than the whole dictionary business. And here's an example where we're going to use a dictionary to populate with different parameters and then pass that to RxD params, brackets parameters, because we have multiple. So params is going to have an alpha entry and a potassium entry, or I'm sorry, it's not potassium, it's just K in this context. But you see that follows very much the same syntax as the states or species. You specify the region, the name, and value or initial or something like that. And for parameters, it's value. For species, it's initial. Here's that second parameter. And here's a little bit more complicated. So we have to define the species. In Neuron, we defined the species without bothering to set the initial value. And then we wrote this function to say that if we're on a segment that is less than half the distance along the section, return 1 millimole for the concentration, otherwise set the concentration to 0. And then we set y initial equals this function my initial. We don't get the luxury of doing things in that order in NetPyNE. So instead, in NetPyNE, we define the sort of functional string that translates from this. So y if node.segment.x is less than a half, else 0. So means the same thing. And then we pass that to the initial value in the dictionary. So just down here. And then finally, we have the definition of the rate. Again, we use a separate string to define the rate equation. And then when you create the dictionary, you give it a name. You decide, you say what species does this rate apply to, and then you define the rate dynamics itself. And then here is the running and plotting portion of that example that we saw the other day. So, the prompt for the problem was to plot the concentration of y versus position at a number of time points to show the development of the traveling wavefront. This can be achieved in Neuron with range-var plot. However, NetPyNE doesn't have range-var plot built into it as far as I'm aware. So we have to do a little... Yes, exactly. But things like this will continue to come up as you go on your NetPyNE journey. So it's useful to know how to sort of use some of the underlying Neuron objects or structures in conjunction with your NetPyNE model. So here the value that, or the variable that we're concerned with for the range-var plot is y, which is a species in this model, if we remember. But if you go through and, I don't know if this has been explained already, but in NetPyNE, you could do sim dot, I think it's create, simulate, analyze. This can be broken up into a number of subsets. So here we've broken it up into initialize, create the populations, create the cells, connect the cells, add the stems, add all the RxD stuff, set up all the recordings, but don't simulate and don't analyze it. So before we simulate it, we import Neuron or import H and RxD from Neuron, as well as matplotlib, so that we can play with some of the stuff that NetPyNE has created for us, but that we don't necessarily have direct access to. So after running that simulation setup code above, even though NetPyNE has created a species called y, y is not a variable that refers to anything yet. So here we've said y is going to be equal to RxD has a list of species under rxd.species, and then it's hidden, but there's an underscore all underscore species. And since I know that there's only one species in this model, I can do bracket 0 because it's going to be the first entry for sure, because there's no other entries. And this open close parentheses is to instantiate it. So this is without the bracket, the open and close parens, This is like a weak reference, so I want to instantiate a weak reference to the species Y and call it the variable Y. So then, if everybody, and hopefully everybody remembers from range-var plot, you specify like a path over which you want to measure this. We want the path to be from the beginning of the dendrite section to the end. So we use the segment dend parentheses 0, the initial segment of the dendrite, and den parentheses 1, that's the final end terminal section of the dendrite. And we can refer to these with NetPyNE by using the sim object. So sim stores a net object, which stores a list of cells. There's only one cell in this model, so we want to look at cell 0 because this is a list. Each cell contains a dictionary of sections. We know, a dictionary of sections. This one's called den, so that helps. And then we want to use the H object entry in that den dictionary. And the H object is a section, a neuron section. So in some ways, neuron sections are like the atomic operators or atomic units, something, for NetPyNE. And we can then refer, so what if I have this without the parentheses 0, this refers to that neuron section, and by placing parentheses 0, close parentheses, that refers to that same segment as we see back here. Hopefully that makes some sense. Similarly, we can refer down to the H object to get that dend parentheses 1 in sort of a NetPyNE format to refer to that segment as well. And then, yeah, I actually should have put the plot here to prove it to you, but I don't know. You can go back and play with the exercise yourself, and that's the plot that comes out. Or the plotting works the same in both contexts. Actually, it's also worth noting that I'm not going to use, I'm not using the NetPyNE convention to sim.simulate and sim.analyze to do my simulating and plotting. I learned that there is some way to do a continue run in NetPyNE, but I don't recall. That's okay, because you can use Neuron as well. So in the same way, I am looping over a series of times and colors and using h.continue run, just like this was a Neuron exercise, to do my sim and plotting. So we set up the network and all of the reaction diffusion stuff with with NetPyNE, but we're still doing our plotting with Neuron and matplotlib. Okay. The last thing we're going to take a look at is this batch RxD example. So we're going to look at how intracellular calcium dynamics can influence network dynamics. So this is all adapted from a paper from 2015 by Sam and I don't know who else was on it. Bill, obviously, Robert, some other people, I'm sure. And so the network model here presented here is like loosely based on the cell model from that study, and that's also where this figure comes from. But the details aren't important. The main gist is that neurons contain intracellular IP3. When IP3 or calcium binds to an IP3 receptor, calcium is released from the endoplasmic reticulum. This results in calcium-induced calcium release, and then the level of intracellular calcium is going to change the neuron state, and by changing the state of a bunch of the neurons in the network, that changes the state of the network itself. So don't pay too much attention to all the code. I'll make the. Oh, I should actually copy that into the chat. Here, bear with me. I'll copy the. I'll copy the IPython notebook into the chat, so you guys can open that up. Share. Meanwhile, anybody have any questions? Oh, I can't post in general. Okay, sorry about that. So, if you guys want, you can open up the Colab notebook and have a look at this yourself, but just a sort of cursory overview. We're going to have 6 cell populations. 3 of them are excitatory, 3 are inhibitory. They all have Hodgkin-Huxley type cell models. And the network is wired in a way such that inhibitory cells innervate excitatory cells innervate everything else, including themselves, or other excitatory cells, I should say. And then for the RxD stuff, we have 4 regions. So there is the cytosol, the endoplasmic reticulum, and the cytoplasm endoplasmic reticulum membrane. And we also have the extracellular space defined. So these 3 are all intracellular, and this is the extracellular space that defines the space between them. We're only going to follow 2 species, calcium and IP3. All the other stuff is taken care of with the Hodgkin-Huxley mechanisms. We have 1 state, which is the state of the IP3 receptor gate. And we have 3 channels. So there's this circa, I'm not quite sure what the pronunciation is. And that mediates a reaction between calcium in the cytosol and calcium in the ER. So this is like uptake of calcium from the cytosol into the ER. There's also a calcium leak from the ER to the cytosol, as well as this IP3 receptor reaction, which is this ligand-gated channel that allows calcium from the ER to leak into the cytosol. And those are defined by these equations above. Don't get too wrapped up in the dynamics themselves unless you're really into this. And then finally, there's 1 rate that affects the IP3 receptor gate. And then we can have a quick look at the code for this. Done. Okay, so I don't think we need to quite rerun the whole thing, but so we install pip and Neuron, get rid of a NetPyNE repository, or get rid of the. So this line is just in case there's already something called NetPyNE, get rid of it. And then we're going to clone a specific branch of the NetPyNE repository. I got to talk to Salvador. Hopefully we can actually just like put this example in the NetPyNE course Git repo. But for now, this is what works. We enter that repo directory, check what's in there, compile all the mod files, create directories for the output data, and then here's the sort of important part where we set up the batch run. Oh, for Christ's sake, I'm sorry, I didn't even explain what the motivation was. So the idea is that we're going to look at how do different combinations of initial IP3 concentration and IP3 receptor density affects local field potential oscillations or network state to some degree. So we'll see what the idea for all this is that we're going to run it for these different combos of initial IP3 concentration and IP3 receptor density, and then see what is the peak oscillatory frequency in one of the LFP electrodes. So this function, batch RxD, sets up it contains a list of initial IP3 concentrations. Since we're going to run these in serial, keeping the numbers small, or the length of the list small, so we're only looking at 0 and 1 millimole, and we're only going to look at 2 densities for the IP3 receptor. So we set those up as our params. The init config is just going to be the duration of the simulation. We call the NetPyNE batch function with this params and this init config. We're going to save it in something, data/batch RxD. That's our output folder. And then we're going to run this run our simulation with these different combinations of initial conditions. Excuse me. So just look at the output. It does all of its running. Things seem to go well. We can check the output. So we've saved the configuration files and the data files. The ones that don't say CFG are output data. And then here, this isn't really hardcore NetPyNE stuff. This is more just using JSON to open up the output files. We look through and find the LFP recorded from the third electrode, because that's the one that I think looked the nicest. Do some demeaning, compute an FFT, find the peak frequency of the power spectrum, and then place that in an array, and then we stick that in a pretty little heat map. And what we can see is that, with low density and a millimole of initial IP3, you get like 2.5 hertz is the prominent frequency in the local field potential. If we bump the density up by 100%, that frequency goes up to something more like 5-6 hertz. But if the initial IP3 concentration is 0, then we end up with a much higher sort of beta range 20 hertz oscillation. And as I mentioned, so this is running in serial right now, so that's why I kept the list small. If anybody's really interested, they can fill out these 2 lists, init list and GIP3R list, with more variables, and they can do a nicer, bigger parameter search with MPI and stuff like that, as long as you can get MPI set up on your own machine. And yeah, that's about it. Totally under time. Hopefully nobody minds. Anybody got any questions? No? One other thing that didn't really fit anywhere that I do want to mention, just briefly, is where was that? So when you do set up the RxD with sim.net.add_RxD, you can specify the number of threads you want to use to do your extracellular space computations. The extracellular diffusion stuff is repeated on all the nodes that you run it on, but the more threads you use, the faster it'll go. So that's a convenient little thing. I think I sped up each batch by 5 or 6 seconds by using 4 threads rather than 1. So, huge improvements. But yeah, okay. Well, thanks, guys. Thanks for your time. Much appreciated. I hope I didn't throw the schedule off by finishing early.
Thank you.
Thanks, Craig.
Thank you.
Thank you.
Yeah,
Thank you.
Salva, you might as well stop recording. Are you here?
Oh, thank you, Sonia, for pointing out voxel size when I couldn't think of the word. Much appreciated.
Salva, go ahead and stop recording now. Otherwise, I'm going to have to edit this video.
He fell asleep, Joe.
Yeah, I know.
Oh, that wasn't your fault. That wasn't your fault, Craig. Right? It was fun. It was interesting. Maybe
No, it's a good talk, Craig. Thanks, buddy.
Call him on the phone. It was a good talk.
Yeah, so I'm trying to get a hold of Salva also to discuss the next session. We already put Craig in front of my original session, and I was going to do this one coming up. But our batch stuff still needs a lot of work, a lot of improvements. When I first joined the lab working with Bill, I was working with this EEE project, and I did a lot of batch analysis. And I made some nice code that sort of put any 2D batch into one big figure, which is nice, and I can show those off. But unfortunately, in the 4 or 5 hours I devoted to this, I was not able to update it to work with the latest NetPyNE. But I will do that this weekend, and then we'll be able to see cool figures from batches. Salvador, yeah, still not back.
I'll try to phone him.
Yeah.
Sorry, yeah, I'm here.
Oh yeah, might as well stop recording first of all, and then.
Okay. Yeah, sorry, was in a meeting.
Deep in thought about.
And then the question was, Salvador, unfortunately, I did not get my batch analysis code updated in time, so I can show